For the last 2 years, the story of AI has been simple. Bigger data centers, more GPUs, more money. Every headline about artificial intelligence has followed the same shape. A company announces a new model. Then it announces how many billions of dollars it spent building the data center that trained it. Then it announces the next data center, even bigger, even more expensive, because apparently that is just how progress works now. But what if that story just broke? What if the next leap in artificial intelligence doesn't come from a bigger data center, but from a machine that barely sips power compared to one? What if the entire industry has been racing in one direction, spending hundreds of billions of dollars building bigger and bigger warehouses full of graphics cards, while a completely different kind of machine was quietly proving that the whole approach might not be necessary at all? That is the claim making its way through corners of the tech world right now. A quantum computer, paired with a novel error correction method, reportedly helped train an AI model that performed comparably to today's most advanced GPT-class systems. The twist is the cost. Not twice as efficient, not even half the price. Roughly 1/10 of the compute resources that a traditional GPU cluster would have needed to reach the same result. If that number holds up, it is not a minor efficiency gain. It is the kind of number that rewrites industry roadmaps, spooks investors, and forces multi-billion-dollar infrastructure bets to be reconsidered from the ground up. Before we go further, let's be honest about where this stands. This is not a peer-reviewed announcement from IBM's press office. It is not a joint statement from Google DeepMind. It is a claim that surfaced through a research write-up, describing a paper that reportedly came out of a joint effort between a quantum hardware team and a university lab in Zurich. The details are still filtering out. Some of it is genuinely exciting. Some of it deserves real scrutiny. And a lot of it depends on exactly what was measured, what was compared, and what was left out of the headline. So this is not going to be a victory lap for quantum computing. It is going to be an honest look at what actually happened, why it matters even if the boldest version of the claim turns out to be overstated, and why the underlying trend it points to is very real, whether or not this exact number survives peer review. Let's start with the part of the story that is not in dispute. Training frontier AI models has become absurdly expensive. When OpenAI trained GPT-3 back in 2020, it reportedly used enough electricity to power over 100 average American homes for a year. That was considered a staggering number at the time. Today's frontier models make that number look quaint. Modern training runs stretch across tens of thousands of GPUs, running for weeks, consuming electricity on a scale that rivals small cities. The financial cost has followed the same trajectory. Training runs that used to cost a few $1,000,000 now cost hundreds of millions. Some estimates for the next generation of frontier models put the number well into the billions. And it is not just the training that costs money, it is the data centers themselves, the land, the cooling systems, the power purchase agreements with utility companies, the specialized chips that take over a year to manufacture and are back-ordered the moment they ship. The entire AI industry has essentially become an infrastructure industry wearing a software costume. This is why every major AI lab has spent the last 18 months signing deals that would have sounded like science fiction a few years ago. Multi-billion-dollar agreements with power companies. New nuclear plants being proposed specifically to feed AI data centers. Entire regions of the country being reshaped around the electrical demands of a handful of hyperscale computing campuses. A single rack of the most popular AI training chips draws well over 100 kilowatts. And the next generation of hardware is expected to push that even higher. A full-scale AI campus can run tens of thousands of these racks, consuming hundreds of megawatts, with some facilities projected to eventually draw a full gigawatt, which is roughly the output of a nuclear power plant, dedicated entirely to training and running AI models. That is the backdrop against which this quantum claim is landing. An industry that is already straining against the physical limits of the power grid, still betting that the answer is simply more of the same, just bigger. So when a research write-up claims that a completely different kind of computer trained a comparable model using a fraction of the resources, it is worth paying attention, even with appropriate skepticism. Here is what reportedly happened. A team used a processor with roughly 1,200 qubits to perform something called quantum-enhanced neural architecture search. That phrase sounds intimidating, so let's break it down in plain language. When engineers build a neural network, one of the hardest and most expensive parts of the process is not actually training the model on data. It is figuring out the right shape for the model in the first place. How many layers should it have? How should those layers connect to each other? What size should each component be? This is called architecture search, and traditionally, it is done by training thousands of slightly different versions of a model, comparing their performance, and gradually narrowing in on the best design. That process alone can consume enormous amounts of compute, because you're essentially running miniature training experiments over and over again just to figure out what shape the final model should take before you even begin the real training run. This is the part of the pipeline where quantum computers may have a genuine structural advantage. Searching through a massive space of possible architectures is fundamentally an optimization problem. You're trying to find the best combination out of an almost incomprehensibly large number of possibilities. Classical computers explore that space one path at a time, or in limited parallel batches, constrained by how many separate configurations they can test simultaneously. A quantum processor, because of how qubits behave, can represent and explore multiple possibilities at once in a way that scales completely differently. In theory, this means that a well-designed quantum system could search through architecture possibilities exponentially faster than a classical one, particularly as the search space grows larger. According to the write-up, the team used their 1200 qubit processor to complete architecture optimization in a matter of hours, a process that would have taken weeks using conventional methods. Once the architecture was selected using the quantum system, the actual training of the model happened the normal way, on classical hardware, using the newly optimized design. This is the detail that matters most, and it is the detail that tends to get lost when headlines compress a nuanced technical story into a single dramatic number. The quantum computer did not train the AI model in the way people typically imagine when they hear that phrase. It did not replace the GPUs. It did not run the actual learning process, where the model adjusts its internal parameters based on data. What it reportedly did was compress one of the most expensive preparatory phases of that process, the search for the right architecture, into a fraction of the time and resources that phase would normally require. Because that phase can account for a significant portion of total compute spend on a large training run. A genuine breakthrough, there could still produce a real and meaningful reduction in overall cost, even though it is not the sweeping total replacement of GPU infrastructure that the more sensational headlines imply. Why does this distinction matter so much? Because it changes the conversation from, quote, quantum computers can now do what GPUs do, end quote, which is not accurate and probably will not be accurate for a long time, to something more precise and, frankly, more interesting. Quantum computers may be extraordinarily good at a specific category of problem that happens to sit inside the AI development pipeline. And if that is true, the future of AI infrastructure might not be a choice between quantum and classical computing at all. It might be a hybrid system where quantum processors handle certain specialized tasks like architecture search, optimization, or high-dimensional sampling, while GPUs continue to handle the raw statistical pattern matching that neural networks are fundamentally built on. Multiple analysts covering the space have converged on almost exactly that framing over the past year, describing quantum processing units sitting alongside GPUs inside the same data centers, handing off specific workloads between them rather than competing head-to-head for the same job. That framing is a lot less dramatic than the headline you might have seen. But it might actually be more important because it describes a trend that seems to be gathering real momentum across multiple companies and research groups rather than a single contested claim from one paper. NVIDIA itself, the company that has arguably profited more than anyone from the current GPU-driven AI boom, has been investing in quantum-adjacent technology, releasing open-source AI models specifically designed to manage the errors that plague quantum hardware, and describing a vision of what it calls quantum GPU supercomputing, where the two technologies work together rather than in competition. That is a notable signal. If the company that dominates AI training hardware is quietly hedging by building bridges to quantum computing, it suggests that even the most GPU-invested players in the industry see a future where quantum systems play some meaningful role, even if that role is narrower than what the boldest headlines suggest. Now, let's talk about why the error correction piece of this story matters so much. Because it is arguably the more significant development, even more than the specific 1/10 cost figure. For decades, quantum computing has been held back by a fundamental problem: noise. Qubits are extraordinarily fragile. The tiniest environmental disturbance, a stray vibration, a fluctuation in temperature, even cosmic radiation, can cause a qubit to lose its quantum state, a phenomenon called decoherence. This has meant that quantum computers have historically been able to perform calculations for only very short windows before errors accumulate, and the results become unreliable. For years, progress in quantum computing was measured mostly in laboratory milestones, more qubits here, slightly longer coherence times there. Interesting for physicists, but not something that translated into practical everyday computing power. What changed, according to multiple sources covering the space over the past year, is that error correction techniques have crossed a meaningful threshold. Google's Willow chip demonstrated what is called below-threshold error correction, meaning that as the system scales up and adds more qubits, the error rate actually goes down rather than up, which is the opposite of how quantum systems have traditionally behaved. Around the same period, another major quantum computing company demonstrated error-protected logical qubits operating beyond what is known as the break-even point, essentially proving that a quantum system could maintain useful, stable computation for long enough to be practically useful, rather than just theoretically interesting. These are the kinds of milestones that quantum researchers have been chasing for the better part of 2 decades, and their arrival roughly coincides with the timeline of this AI training claim. That is not a coincidence. It is very plausibly the reason the claim exists at all. Without meaningful error correction, a 1200-qubit processor attempting something as complex as neural architecture search would almost certainly produce results too noisy and unreliable to be useful. With it, the door opens to exactly the kind of demonstration being described here. So even if you set aside the specific 1/10 number and treat it with the skepticism it deserves, given how early and unverified this claim still is, the underlying trajectory is worth taking seriously. Quantum hardware is becoming more stable. Error rates are dropping in ways that were considered a distant hope just a few years ago. And AI companies are actively exploring, in public and in job postings, how to fold quantum processing into their existing infrastructure rather than treating it as a separate, competing technology. Google has reportedly posted openings for quantum researchers, specifically focused on building AI-based discovery pipelines. That is a very specific, very telling kind of hire. It suggests that at least some of the largest AI labs in the world are not waiting around to see if quantum computing becomes useful. They are actively trying to figure out how to use it right now in narrow, targeted ways, while the broader technology continues to mature. There is another angle worth considering here, one that rarely makes it into the more sensational coverage of this topic. The economics of AI development are not just about the cost of the final training run. They are about the cost of everything that leads up to it, including all the failed experiments, the abandoned architectures, and the dead ends that never make it into a published paper. For every model that gets released to the public, research teams typically run dozens, sometimes hundreds of smaller experiments trying to figure out what works. Most of those experiments never see the light of day. They are simply the cost of doing business in a field where progress often comes from trial and error at a scale most people outside the industry never see. If a technology can meaningfully compress that trial and error phase, the savings would not just show up in the cost of the one final model that gets announced. They would show up across the entire research process, in every lab and every company running these kinds of experiments, which is exactly why a genuine breakthrough in this specific part of the pipeline would matter so much more than its narrow technical description might suggest at first glance. Let's talk about the skepticism this claim deserves, because a responsible look at this story has to include it. First, extraordinary claims require extraordinary evidence, and right now the primary source for this specific 1/10 cost figure appears to be a single write-up summarizing a paper, rather than the paper itself being widely covered, replicated, or verified by independent researchers. Major results in AI and quantum computing typically go through a period of scrutiny, where other labs attempt to reproduce the findings, where the methodology is picked apart, where the specific benchmarks used to measure comparable performance are examined closely. Comparable to GPT-class systems is a phrase that can mean very different things depending on what specific benchmarks were used, how large the model actually was, and what baseline it was measured against. A small model that performs well on a narrow set of tasks is a very different achievement than a model that matches the broad, general capabilities of the largest frontier systems currently available. Until the actual paper, the actual benchmarks, and the actual methodology are available for outside researchers to examine, the responsible position is cautious interest rather than confident celebration. Second, it is worth remembering that this technology story is unfolding inside an environment that has enormous financial incentives to produce exciting headlines. Quantum computing companies are, for the most part, not yet profitable in any meaningful sense. Their stock valuations are driven heavily by narrative and by promises of future breakthroughs. A headline suggesting that quantum computing just solved one of the biggest cost problems in the entire AI industry is exactly the kind of story that moves markets, attracts investment, and generates enormous attention, regardless of how precisely accurate the underlying technical claim turns out to be. That does not mean the underlying research is fabricated or dishonest. Serious researchers can produce a real meaningful result and still watch it get inflated, oversimplified, and stripped of nuance as it travels through blog posts, social media summaries, and eventually video scripts like this one. The job of anyone trying to understand this space honestly is to separate the signal from that noise, to ask what was actually measured, and to resist the urge to round every incremental advance up to the word breakthrough. With that caution clearly on the table, let's zoom out and talk about why this story, even in its most conservative, most heavily caveated form, still points towards something genuinely important. The AI industry is running into a wall that has nothing to do with algorithms and everything to do with physics and economics. You cannot infinitely scale data centers. Power grids have real capacity limits. Chip manufacturing has real supply constraints. Water for cooling has real availability limits in many regions. Capital, even at the scale the biggest tech companies are currently deploying, is not infinite, and shareholders eventually start asking hard questions about return on investment when a company spends tens of billions of dollars building infrastructure that may or may not pay for itself. Every one of these constraints is pushing the industry to look for efficiency gains anywhere it can find them. And quantum computing, even in its current, early, narrowly applicable form, represents one of the few genuinely novel approaches on the table, rather than just another incremental improvement to the same GPU-based approach that has dominated the last decade. This is where the phrase GPU data centers can't compete deserves a careful, honest examination, because, taken literally, it is almost certainly wrong, at least for the foreseeable future. GPUs are not going away. They are not being replaced wholesale by quantum processors anytime in the next several years, and probably not for a long time after that. The vast majority of what makes modern AI systems useful, the statistical pattern recognition, the language understanding, the image generation, the actual moment-by-moment process of a neural network processing information, runs on architectures that classical processors, and specifically GPUs, are extraordinarily well suited for. Quantum computers are not general-purpose replacements for that kind of computation, and nothing in the current research suggests they are on a path to becoming one anytime soon. What they may become, however, is an increasingly important specialized tool sitting inside the same infrastructure stack, handling the specific categories of problems where their unusual computational properties give them a genuine structural edge. Optimization, certain kinds of sampling, simulating quantum systems themselves, which has obvious applications in chemistry, materials science, and drug discovery. And now, apparently, at least according to this early and still unverified claim, potentially neural architecture search as well. If that hybrid picture turns out to be accurate, then the real headline is not that quantum just beat GPUs at their own game. The real headline is that the AI industry may be on the verge of a meaningfully more efficient way of building models, one where the most computationally expensive design decisions are handled by a fundamentally different kind of machine before the heavy lifting of actual training even begins. Even a modest, well-verified version of that story would still represent a genuine shift, because architecture search and hyperparameter optimization are not small line items in a modern training budget. They can represent a substantial share of the total compute spent on developing a new model, particularly as companies experiment with dozens or hundreds of candidate designs before settling on the one that eventually gets trained at full scale. Shrinking that phase from weeks to hours, even without touching the core training process at all, could meaningfully change the economics of how frontier models get built. There is also a longer-term implication worth sitting with, one that goes beyond the immediate cost savings. If quantum-assisted architecture search proves out and becomes a reliable, repeatable technique, it does not just make existing model designs cheaper to discover. It potentially allows researchers to explore a much larger space of possible architectures than they ever could using purely classical methods, simply because the exploration itself becomes so much faster and cheaper. That could lead to genuinely novel model designs, architectures that human researchers or classical search methods might never have stumbled upon, simply because the computational cost of testing them would have been prohibitive under the old approach. In other words, the most exciting long-term possibility here is not just that AI gets cheaper to build, it is that AI could get structurally better, discovering more efficient, more capable designs, because the search process itself is no longer bottlenecked by the same constraints that have shaped every major model built over the past several years. Of course, all of this rests on a chain of assumptions that still need to be verified. The error correction techniques need to keep scaling the way early results suggest they will. The specific claim about a tenfold reduction in compute needs to be replicated by other teams, using transparent methodology and comparable benchmarks. Quantum hardware needs to become more accessible and more reliable, moving beyond a small number of specialized research labs and into something closer to standard infrastructure that a broader range of AI companies can actually use. None of that happens overnight, and history has given us plenty of examples of quantum computing announcements that generated enormous excitement in the moment and then quietly failed to translate into practical, widely adopted technology. Skepticism here is not cynicism. It is simply an accurate reflection of how early this specific claim still is and how much verification work remains before it should be treated as an established fact rather than an intriguing, still unconfirmed report. But here's the thing worth remembering as this story continues to develop. Whether this particular paper holds up exactly as described, or gets revised, corrected, or partially walked back as more scrutiny arrives. The broader trend it is pointing toward quantum systems maturing to the point where they can meaningfully assist specific parts of the AI development pipeline is not a fringe idea anymore. It is being pursued in parallel by some of the most well-resourced and technically serious organizations in the world, from major chip manufacturers hedging their bets, to search giants quietly posting job openings for exactly this kind of hybrid research, to specialized quantum hardware companies racing to demonstrate practical advantage rather than just laboratory milestones. The direction of travel is clear, even if the exact timeline and the exact magnitude of any individual claim, including this one, remains genuinely uncertain. So where does that leave us? Somewhere between the two extremes that tend to dominate conversations like this one. It is not true that quantum computing just made GPU data centers obsolete. That framing, however catchy it sounds in a headline, does not hold up against what the underlying research, as currently described, actually claims. But it is also not true that this is nothing, or that it is simply hype dressed up as science. Something real appears to be happening at the intersection of quantum hardware and AI development, even if the boundaries of that breakthrough are considerably narrower than the most viral version of the story suggests. The honest, useful takeaway is this. Watch this space closely, but watch it with your skepticism fully intact. Wait for the underlying paper. Wait for independent replication. Wait to see whether other research groups can reproduce anything close to a tenfold efficiency gain using similar methods. And in the meantime, pay attention to the quieter signals, the job postings, the strategic partnerships, the hardware companies quietly building bridges between quantum and classical systems, because those slower, less dramatic developments may ultimately tell you more about where this technology is actually headed than any single headline ever could. The race between quantum and classical computing was never really going to be a war with one clear winner. It was always more likely to end up as a partnership, however unevenly matched it looks today. And the story unfolding right now may be one of the very first real glimpses of what that partnership actually looks like in practice. Whether this exact paper survives scrutiny or fades into the long list of quantum computing claims that never quite lived up to their headlines, the underlying question it raises is not going away. Can a fundamentally different kind of machine make artificial intelligence dramatically cheaper to build without replacing the hardware that already works? For now, the honest answer is maybe, and maybe, in a field moving this fast, is still worth paying very close attention to.